Hello everyone, I am Deepak Paliwal. So in the previous lecture, we have learned about the stress field around screw dislocation. So in this lecture, we will learn the stress field. We will learn about stress field around the edge dislocation. So the derivation we have done for screw dislocation, and we will not going to derive the equations for the various stress components in the edge dislocation part because the derivation part is very much complicated. So we will use some results to understand the various issues related to the stress field around the edge dislocation. So very first, here in case of the edge dislocation, like in case of screw dislocation, some of the components are zero. Here is also the sum of some components are also zero, like sigma x sigma xz is 0, sigma zx is 0, sigma yz is 0, sigma xz is also 0, or sigma zy is also 0. Okay, if I represent like a tensor sigma ij. Okay, so if I am marking only right sign to those components which are available in case of the stress field in edge dislocation. So here we have marked like these components are present, like the components which are not equal to 0 is sigma xx, sigma xy, sigma yx, sigma yy, sigma zz. Other than that, all other components are 0. Okay, so now the sigma xx value is equal to minus gb divided by 2 pi 1 minus nu is the Poisson's ratio, g is the shear modulus, 3x square plus y square, x square plus y square. X and y represents the position around the dislocations, which we have already seen in case of the screw dislocation. Sigma yy, here the negative sign, here this negative sign showing the compressive stress, positive sign shows the tensile stress. Okay, again the sigma yy is gp 2 pi 1 minus nu y x square minus y square divided by x square plus y square whole square. Sorry, here we also have square of x square plus y square term. Again we have sigma xy, that is equal to the gb 2 pi 1 minus nu is the Poisson's ratio, x square plus y square on x square plus y square whole square. Sorry, this is not plus, this is minus. Okay, so we have sigma xy, sigma yy, sigma xy. Uh, let us see sigma zz. Sigma zz will be equal to mu times of sigma xx plus sigma yy. That should be nu times. That should be nu times. Okay, now let us see the stress distribution or stress field in x and y coordinate, how this particular component sigma xx is distributed in xy coordinate system. So here suppose we have edge dislocation, so the distribution of sigma xx is like this. In the negative direction, both symmetric, both these things are symmetric around x-axis. In case of the sigma yy, in case of sigma. Or here also one point I should mention, like this is the compressive one, this is the tensile one. Okay, so the above the edge dislocation, the sigma xx is giving the compressive stress field, and it is giving a uh, tensile stress field. We will learn how we can know whether it is compressive or tensile. We will learn shortly with the help of these equations only. Okay, now the distribution of sigma yy in the xy reference frame. So it is like, let me take again blue color, like this, like this. Okay, let me rough one, this one, like this. So this is negative, this is positive. Let me mark with the green color. This is positive, and this is positive, this is positive, this is negative. So this is the profile, like the distribution of sigma xx, sigma yy. Okay, now let us see the distribution of sigma xy, sigma xy. It would be like this. Okay, this is positive, this is negative. Then we have petal like this, like this. This will be negative, this will be positive, this is again positive, this is negative. Okay, so here we have sigma xx, sigma xy distribution on xy axis. This is sigma yy, this is sigma xx distribution. Okay, so now some important points, like one more thing important, the hydrostatic component will be minus 1 by 3 sigma xx plus sigma yy plus sigma zz. We know the hydrostatic component is the sum of all the diagonal elements of the stress tensor and divide by 3. So that is your hydrostatic part. If I take a note here, important note here, edge dislocation, stress field poses both dilatational as well as shear stress components. Shear stresses, we can say, edge dislocation consists of both shear stresses as well as a dilatational part. Okay, and again from this equation, if I write in this like in the polar coordinate, and we know the term x square plus y square would be r square. So again the sigma xx or anything sigma yy, if I taken, then it is inversely proportional to 1 by r. Again for r very large, the stresses will be very low, or 0. But in case of r tends to 0, sigma xx sigma yy tends to infinite. So what does it mean? That the again for edge dislocation, for radius r to r naught, this is the radius of core. So the radius, when radius is less than r naught, then this is the region of dislocation core where elasticity assumptions are not valid. That is similar the case with the screw dislocation. Okay, now what I said, like ki where is the compressive stress field, where is the tensile stress field. We will try to understand that one. For that purpose, I am just taking these two equations from here. Let me copy these equations from here to here in order to explain. Okay. Okay, so now let me draw the xy coordinate again. The color is changing from here. Let me unselect that one, and let me draw some line here. Okay, okay, this is my x1, this is my y, this is negative x, this is negative y. Let me draw with it. Here x is greater than y, here x is less than y. Again here x is less than y, but minus y minus x plus y. Okay, here x greater than y, but minus x plus y. Here x greater than y, but y is negative, x is positive. Here x is less than y, here x is less than y, here x is greater than y. So this is the coordinate which I am talking about. Let me draw some boxes so that I will represent the stress field sigma xx and sigma yy. Okay, let us first consider the case that is like x greater than y. We are in the, let me call it, this is the first, this is second. Let me change the color as well. This is first, this is second, this is third, this is fourth, this is five, this is six, this is seven, this is eight. Okay, so now we are talking about for the first one. Here the x is greater than y. Look at the sigma xx equation. Sigma xx for the x greater than y. Okay, so the complete these things will be, this thing will be positive and it has negative sign, so it will be negative only. Sigma yy I am talking about. For the sigma yy, see, the x is greater than y, so again this this whole term, this whole term will be, this whole term will be your positive quantity, so it will be positive. That means if I draw with the black color, like black color. Okay, okay, so sigma xx negative, that means this is compressive stress field, and sigma yy that will tensile one. Now I am talking about in the second case, when x is less than y but both are positives. This one is also positive. Okay, so now x is greater than y. See, sigma xx and sigma yy. Sigma xx, again x is greater than y, both are positive, again it is negative, so this will be negative quantity. Now here the picture comes like y is greater than x. Okay, y is greater than x, that means that will be the negative, so this become negative only, this become negative only. Okay, so sigma xx is negative, sigma yy is also negative, because y is what, y is greater than x, so it, this term becomes negative, and this complete term is positive from the beginning, so sigma yy will be negative quantity, so it becomes like what, both become compressive. This is already compressive, this is also become compressive. Now in case of third one, the case is what, now here y is positive, x is negative. Okay, but y is greater than x. Okay, let's see sigma xx, what will happen with the sigma xx. Okay, now x is less than y but the x is negative. Okay, see the sigma xx value here, Here is the square term, there is no sign, like y is positive, and here a complete term in the square form, so that would be also positive, so this is negative, it has negative sign, so it becomes negative only. But in case of sigma yy, in case of sigma yy, what you can see, like y is positive, y is positive, but y is greater than x, so this complete term is negative, and this is positive, so positive negative becomes negative, so this become also negative, sigma yy is negative. So again, this third coordinate will show this type of stress field. Okay, let me check again, like x is less than y. Okay, so this complete term is positive. Okay, and this is negative, so it becomes negative. Here is what, y is greater than x, so this term becomes negative, and y is positive here, so it becomes completely negative term. So again, here we have negative stress field. Now taken in a fourth quadrant. Fourth quadrant is what, x is greater than y, but x is negative. Okay, and y is positive, so again see sigma xx, sigma yy. In case of sigma xx, in case of the sigma xx, what we can see here, what we can see, like x is greater than y, but x is negative, so here again square term, this all complete term is positive, and y is positive, so this is negative sign, so it will show negative only. But in case of sigma yy, now you can observe x is greater than y, that means whatever happens, okay, it this term becomes positive only, so this is positive only, so this become positive only, so this become negative, and this become positive. Okay, now come to the fifth coordinate. Let me write this is here only. Again, sigma xx, sigma yy we are evaluating, and we are talking about x is negative, y is also negative, but here x is greater than y. In this quadrant we are talking about, in this quadrant we are talking about, so see, x is negative, y is negative, again these all are the square terms, this will be positive, and y is negative here, so negative negative becomes positive, so sigma xx become positive, sigma yy you can see again square term. Okay, and which is greater, x is greater, so this complete term is positive, and since y is negative, so this is also negative. So how we can write here or draw here, let me take different pen. So this is positive, this is positive, so what basically we are doing, we are taking various positions around this location, and we want to deduce what are the stress field direction, like tensile and compressive, in along x direction and y direction. So in the fifth position, sigma xx is positive, that means tensile one, and sigma yy is negative, that means compressive one. See how easily we can deduce, like for the sixth one, again x is less than y, and again negative x, negative y, negative x and negative y, so x less than y. Again see here, all the square units, this will be positive, and y is negative, and negative negative becomes positive, so sigma xx become positive, and sigma yy is what, again see, y is greater than here, so negative sign will be dominate here, and here is already negative sign, negative negative becomes positive, so it will be positive. So this is like what, both side it will give tensile stresses only. Now I will talk about in the seventh position. Here what is the condition? Here x is positive, y is negative, but y is greater than x. Okay, y is greater than x. So what will happen? Let me scroll it down somewhere. We are talking about sigma xx, sigma yy. In case of sigma xx, again see, x is positive, y is negative, okay, and y is greater than x. Again, this is the complete positive term, okay, and y is negative here. So negative negative becomes positive. So sigma xx is positive, sigma y is already negative, okay, and y is greater than x. So this term is negative, this is negative, so this term become positive only. So again it will shows like this side also showing positive both side. But in case of what, in case of eighth position, x is greater than y, x is positive, y is negative, okay. See, sigma xx and sigma yy. In case of what, sigma xx, see, what is the condition? X is greater than y, and y is negative, y is negative, and x is positive. So this complete term becomes positive, and this is negative only. So negative negative positive, and it becomes positive only. But in case of sigma yy, see, the y is less than x, and this is complete positive term, and y is negative, so this is become negative only. So this will give what, tensile along x direction, and compressive along y direction. So in this way, see, let me copy this figure from here, okay, let me copy, okay, can paste it here only, okay, we can move here. So what we can observe here, like at the different position different stress field around the edge dislocation with the help of sigma xx, with the help of sigma xx sigma yy equation, we have deduced this particular stress field around edge edge dislocation, around edge dislocation, okay. Now we will understand about the elastic energy, okay. First we will try to understand the elastic energy in case of screw dislocation, then we will talk about elastic energy in terms of elastic energy for the edge dislocation. Now elastic energy from beginning, elastic energy is associated with like elastic part, like what you mean or what we mean by the elasticity, like whenever we apply the load, the material will deform, and when we remove the load, the material will come to the original shape and size. So we are talking about only in this region. So we want to calculate the elastic energy of dislocation. So like what we know, like energy in terms of stress strain, like 1 by 2 sigma into strain, this elastic energy per unit volume. So similar thing we will use here, similar thing we will use here, okay. So how I can write in terms of uh, tensorial notation, ij is equal to 1 by 2 summation sigma ij epsilon ij dv per unit length. So what we want to calculate, we want to calculate the elastic energy of dislocation, particularly the screw dislocation per unit length of dislocation, per unit length of dislocation. Okay, now this is the general equation for both screw and edge. Now we will talk particularly about screw dislocation. Particularly about screw dislocation. So what, how I can write Dij is equal to 1 by 2. uh, what I need to do, I need to do this summation. Okay, so summation I will do like sigma theta z epsilon theta z sigma z theta epsilon multiply by, let me do rough, epsilon z theta. Now I need to write the volume. How I can write dv, like for screw dislocation what we have seen, like 2 pi r multiplied by dr, and per unit length we are talking about, so the volume become 2 pi r dr. Let me write with a small letter, that will be easy. R is the radius of dislocation and dr. Okay, so both sigma theta z or sigma z theta are equal. Similarly, sigma epsilon theta z is equal to epsilon z theta. So the strain components are symmetric. So d e I j 1 by 2 because 2 times sigma theta z epsilon theta z 2 pi r 2 pi r dr. Okay, so now let me put the value of this uh, this sigma theta z, which we have already calculated in the previous lecture gb 2 pi r, and epsilon theta z is b 4 pi r. This is 2 pi r dr. Let me simplify it further. With 2 to cancel, with 2 pi r would be cancelled with 2 pi r, so becomes gb square 4 pi r dr de. This is the elastic part. Elastic part, we are calculating the energy in terms of elastic part. Okay, so now what we have seen here, gb square 4 pi dr by r de elastic. Okay, so this is the elastic part energy. Now if I differentiate it from 0 to e, and from r naught to r naught we know. Why r naught we are talking about, why we are interested in the r naught, like the dislocation is like if we put the r naught, like let me explain first. Like if I differentiate d elastic part 0 to e elastic, okay, gb square by 4 pi, and this is dr r, this is r naught to r, or r naught to capital R, let's say. This is the notation only. So this becomes E elastic is equal to GB square by 4 pi. This is ln R, that would be R naught to R. So E elastic is equal to GB square by 4 pi ln R by R naught. That will be the final equation. So here R naught is the radius of dislocation dislocation core, where our assumptions are not valid. Okay, and capital R is the radius of dislocation. Radius of dislocation. So this is the equation for screw dislocation. Now we will talk about the equation for edge dislocation. Equation for equation for edge dislocation. Again, I am directly writing the result for the elastic energy for the edge dislocation GB square by 4 pi. We will have only the one additional term, 1 minus nu is Poisson's ratio, ln r by r naught. Okay, this r naught is again dislocation core radius, and r is the capital R is the radius of dislocation, or radius of stress field of a dislocation, that we should say. Okay. Radius of stress field. Okay, the area in which the stress fields are prolonged. Actually, this both stress field around edge dislocation or your screw dislocations are the short range only. Okay, so like this R naught value, this is that represent the radius of a core of a dislocation, is around like b to Berger vector to 4 times of the Berger vector only. Like I am interested in calculating the total energy, and like total energy is the sum of elastic part plus plastic part. So the finally, if I write the expression for the elastic part, like GB square 4 pi, and the this the dislocation, like the energy due to the core of the dislocation contribute to only the 10%. Okay, so sometimes we ignore the energy of a dislocation due to the core region, because the total contribution of the contribution of the energy from the core of dislocation is very less as compared to the total energy is the sum of like elastic plus plastic part. So directly I am writing the equation, I am not deriving it. R by b plus b is constant, or this is coming from the core region. Again, if I make some constant also, then I can write it like ln er by b. Okay, e is again a constant value, and if I assume some arbitrary number, like this radius of dislocation is like 5 micrometer, and b is like 4 angstrom. I am writing this arbitrary numbers, then this ln er by b value is approximately around 8 pi. Suppose if I write this GB square by 4 pi multiplied by 8 pi, so the total energy becomes what? Total energy becomes 2 times of GB square. Okay, or this is a constant number, na? This is only a constant number, so I can write like E total energy stored in a dislocation is alpha times GB square. Alpha is a constant quantity. Okay, alpha varies from 0.5 to what, 1.5. Okay, let me write correctly, from 0.5 to 1.5. And what I was saying that time, like the energy due to core energy due to core energy due to core is less than 10% of the total energy. Like for example, suppose the total energy is 100 joule, so the only 10 joule is the contribution from the core of the dislocation of like dislocation core is contributing only 10% or less than 10% of the total energy. So that's why sometimes for the calculation, for avoiding the complications, we remove the values of energy from the core of the dislocation. Okay, so in this lecture we have learned about the stress field. What we have learned, like stress field around the edge dislocations. Okay, so we haven't derived the equation, but we have seen the results. So we have seen the sigma xx, sigma yy. Okay, and we have also seen the sigma zz, sigma xy expression, how the distributions of sigma xx, sigma yy, sigma xy, and where the dislocations, where our assumptions are failed, and why the model is not working, like are not, when the radius of the dislocation becomes zero, the stress field becomes infinite. So at that position our elasticity assumptions are not valid. So there is a reason, from there is a reason of radius r naught, which represent the dislocation core. Okay, then we have seen this various positions, the stress field, or nature of the stresses acting on elements uh, at different locations around the edge dislocation. Okay, then we have seen the elastic energy of edge dislocation and the screw dislocation. And finally we have seen that the elastic energy due to the core of the dislocation is contributing very less. So for avoiding the complications in the calculation of the total energy, sometime we also avoid the energy of a dislocation core. Okay, so in this lecture we have learned about all these things. So we will learn new some new aspects of the deformation mechanisms of FCC material in the next lecture. So till then, bye bye, and thank you for the watching my video. And if you are liking these videos, please do subscribe and give a thumbs up. And thank you for watching this video.